So I guess we're going to be getting restarted now. If people want to gradually make their way to their seats. Should probably move the slides. So the next phase of this morning's events is moving to a campus collaboration showcase. What? Perfect. Thank you. The campus collaboration showcase that is an effort to show some of the ways in which the SEI and what sometimes gets referred to as main campus, this part of Carnegie Mellon, is the ways that we're starting to build collaborations and interactions that stretch across the two parts of the institution. So my name is David Danks. I am probably the only philosopher speaking at this thing. I think I might be the only philosopher ever to speak. It's unclear. There have been others. And you might think that I'm here to talk about, say, ethics and AI or technology and its impacts on society, which is actually work that we're starting to try and set up as a collaboration involving people at SEI and those of us over on main campus. But that's actually not what I'm going to be talking about today. Instead, I'm going to be talking about a collaboration that's developed over the last 3 years with some folks at SEI centered around the challenge of doing causal discovery, causal learning, being able to understand how the world works from data, not just being able to predict what the world is going to do. So in particular, there's a kind of, I think, standard distinction that people draw, correlation versus causation. It's something that I think we all are acutely aware of in our everyday lives. In terms of thinking about some of the mission-relevant questions that we would want to ask at SEI or in the DoD more broadly, we can ask, for example, if we have a group of warfighters that are involved in training, we might want to ask a correlational question, a predictive question, such as how can we predict their performance given what we know about their training? So we're not trying to change anything. We simply want to predict the way that the world is actually going to evolve when we don't change it in any way. And we can do that using purely correlational information. Deep networks were mentioned at the end of the last talk. Deep networks are a correlation-based, statistics-based, prediction-based system. What they do is they can extract the statistical structure of the environment and use that to make sometimes quite accurate predictions about what will happen as the system evolves forward in an unperturbed way. But of course, we might instead want to change the training. We might want to be able to intervene on the system and change it in some way. And to do that, we need to have causal knowledge. Because just as you can't fix a disease by intervening on the symptoms, even though you can predict a disease by intervening on the symptoms, you might be able to predict warfighter performance given their training, but the predictors might not be the sorts of levers that we can use to change their training. Or to use a non-DoD, well, I guess it is health-related example, one that we've also worked on. Consider the case of breast cancer. We can use standard statistical machine learning methods to try to predict the way the cancer cells will develop, but in many cases what we actually want is the ability to develop novel treatments. We want to be able to intervene on the cells and change the way that they're going to evolve. And again, we need to be careful that we don't intervene on symptoms rather than the underlying causes. So we need to be able to extract causal information somehow for lots of the questions we want to ask. Now, as we all know, if you've taken an intro stats class, correlation is not causation. You know, maybe it helped. The interesting thing, though, that isn't usually talked about in statistics classes is that correlation is actually correlated with causation. So you can't make a simple, straightforward inference from a correlation to a causal relation. Just because two things are correlated does not mean that one causes the other. There could be a third factor that causes them. There could be sample selection bias. There are lots of explanations for it. But when we look at patterns of correlation, we can often find that there are small numbers of causal structures that could possibly have produced those patterns that we see. So we have an idea. This is an idea that was first raised in the 1920s by Sewell Wright, a geneticist, and has continued to be explored in various ways, and the pace has accelerated in the last 30 years, looking at the possibility that we could start from data and actually get causation. The sort of holy grail that you're told in statistics class you can't get. The question is, perhaps maybe we could do better and we could find ways to do it. So that's been the topic of a major research project over the last 30 years here in philosophy of all places. If you're curious, come talk to me afterwards and I can explain why we have a philosophy department that does AI. Well, it's Carnegie Mellon, what did we expect? And it's stretched across a wide range of colleagues, graduate students, former collaborators, researchers, and the basic strategy that we've pursued over the past 30 years has been to start by giving a language, a way of talking about causation in the world, a language that we can use to express what it is for one thing to cause something else, not in some necessarily deep philosophical sense, though it has those implications, but in a rather operationalized way that connects to this idea that causation is about controlling the world, that if C causes E, then wiggling C is a way to bring about changes in E. And once you have that sort of a language, you can define a whole set of reasoning and inference and prediction algorithms that enable you to go from the causal structure to data. Whether it's predicted data, observational data, counterfactuals, what would have happened if the buses had broken down in Pittsburgh this morning? I would have been late. What would happen if we were to change, moving forward, the training procedures that we use for our warfighters? But if you've got that, if you've got the ability to predict and reason about empirical data, counterfactuals, hypotheticals, given a causal structure, we can actually invert that relationship. And that's the key to causal learning and discovery, is that we start from data and we work our way backwards to ask, what are the causal structures that could plausibly, or even possibly, have produced data that look like these data that we have in front of us? So that's the general strategy that we've pursued. And in practice, that leads to suites of algorithms. So we've got algorithms we've got a whole language for representing causation. It turns out to be one that you can, based on what are called graphical models, nodes and arrows, you can teach it to an undergrad in about 30 seconds, and they can then proceed to do all kinds of work. We do this in our classes. We can get somebody to be able to do causal discovery in about 25 minutes. They're CMU undergrads, they're smart, but we can do it quickly. The outputs of these algorithms are these causal graphs that are very easy to interpret. So all the worries that you might hear about AI, we need explainable AI, we need transparent AI, we need interpretable AI. You get that for free with these kinds of causal discovery methods. We also can do not only representation, we can do reasoning and inference in a very computationally efficient way. We can generate predictions. In fact, when we first coded it up, we realized we had a user interface problem. We generated the predictions so fast that the users thought we were making things up. So we had to stick in a little bar that made it look like it was taking a long time because they couldn't believe we could do it as fast as we could. The joys of user interfaces. And of course, causal discovery. We can go backwards. And all of these have been implemented over the last 30 years in a software package, open source, reasonably well tested, though certainly not hardened to the extent that folks at SEI are able to do with their software, called Tetrad, and that we make available and that has now been being used in quite literally hundreds of groups around the world. Now, you might wonder what are the problems that we can handle, because there's always limits to what you can do when you develop new machine learning or AI algorithms. So of course we can handle the simple cases. This was the work that was done about 25 years ago, 28 years ago, basically figuring out how to do causal discovery in the nice, simple case where you get to observe all the things you care about. But of course, that's not the reality in any application. It is never the case that you're able to observe all the things you care about. It's never the case that you have all the data you want. Sometimes you're going to have unobserved common causes. Sometimes you're going to have selection bias. And in fact, we're able to do causal discovery even in the presence of those kinds of complications. In fact, what we've pursued over the last 35 years has been a series of investigations where we've succeeded in extending the scope of causal discovery far beyond the simple case. We can do causal discovery from hundreds of data sets. We can do that don't all measure the same variables. We can do causal discovery given time series data that's coming in at essentially real-time speeds. We can do causal discovery with over 1 million variables. And so what we've been able to do is expand the scope and at the same time, the applications that we're applying them to. So as an example of the kinds of applications, I'll give you two very quick biological examples. One is, suppose you wanted to understand the causes of Spartina grass growth down in the Cape Fear estuary in North Carolina. We got data, fairly small data set, and you used our algorithm, and what came out of the algorithms is they said the only thing that matters of the things that were measured is the pH level. Other things are relevant, but always mediated by pH. And we thought this was really surprising. It seemed to go in the face of a lot of the prior expert knowledge that we were finding in the literature. Well, lo and behold, it turned out somebody had done greenhouse experiments and confirmed pH is the only thing that matters. But that news had not made it out to the rest of the community. So we had this validation. This was one of the very first applications we'd done. Much more recently, there was an application looking at the causes, the genetic causes of the flowering of the Arabidopsis flower, shown there. And this was a very hard problem because, in fact, we had over 21,000 genes and we had 47 data points. Usually, if you're doing, for example, regression, they tell you you want 5 times as many data points as you have variables. We didn't know what we were going to be able to get out of this. Anything you could figure out would be helpful. And what, in fact, the causal discovery algorithm said is it said, here are 9 good candidates for what might be the regulators of the flowering time for the Arabidopsis flower. Turned out, after subsequent greenhouse experiments, 4 of the 9, in fact, were. Now, you might look at that and say, wow, 44% success rate? That's pretty bad. Except, if you compare it to 4 out of 21,000, it looks a whole lot better. And that I wanted to make sure to bring up, because it's an important moral about not only causal discovery, but all AI and machine learning applications. They all are what in philosophy speak we would call defeasible. They're going to give you partial information. They're going to give you more information than you had before, but you shouldn't think of these as black boxes that simply deliver the truth to you as if it came from on high. Rather, the way to think about these is that they are tools by which you can start to understand the world around you a little bit better. So what have we done in collaboration with the SEI? Well, over the last 3 years, we've really pursued, along several different projects, which my collaborator Bob Stoddard is going to talk about just after this, we've really pursued things along the following kind of schema. First, we've talked to people like Bob and others at the SEI to figure out what are the challenges that SEI faces. I should mention I also do some other work with the DoD and the IC that is not through SEI that is similar. You have to sit down and talk to people and find out what their challenges are. And then, in many cases, it turns out we already have algorithms that would apply to the particular challenge that that customer, that agency faces. In which case, we've got a very interesting problem in applied machine learning, which is how do you actually use these algorithms in collaboration with the domain experts to try and extract the kinds of information that can help them design better interventions, design better policies. At the same time, the problems that many of you in this room face are far more interesting than anything I can dream up in my philosopher's armchair. I can sit there and I can think about what's an interesting problem. And then I talk to the people who are out in the real world, not here in the ivory tower, and I discover that the challenges that are out there in the world are so much more complex than anything that we think about when we're just doing it all on our own. And so oftentimes we find we don't have an algorithm that works perfectly. But that's an opportunity for an incredible research challenge now. How do we come up with a new algorithm that will actually solve the causal discovery problem that this collaborator, this partner, faces? And the important thing for both of those is that we end up with exciting research problems. The collaborations that are going on in this space between us in philosophy and machine learning and the folks in SEI is a two-way street. This isn't, we've got the knowledge and we merely dispense it to folks at SEI. We are learning just as much. I think we're learning more. Bob might disagree. But we are learning so much by collaborating with the SEI folks that this has been a really wonderful collaboration for me as somebody who's not an SEI staff person. As somebody who is new to this whole world of software engineering, it's been incredibly exciting for us to get a whole new set of research problems and to be able to work with such wonderful people, one of whom I'd now like to bring up, Bob Stoddard, who will talk about, from the SEI perspective, the way that this collaboration has gone.
Thank you, Dave. So I'd like to echo that we've really appreciated the research collaboration opportunity with David Danks and the Department of Philosophy. They've really accelerated our learning curve on the discovery algorithms and on the tooling. And so we've been able to use that as a tool in our toolkit to go apply it to research problems in our SEI focus. So today I wanted to carry on with what Dave was saying and talk about the benefits of this relationship. We have 3 active projects, 2 are restricted, so I'm going to have my comments today related to the one that's fundamental research. And so basically the active research project is fundamental research is called SCOPE, and it is about controlling software costs rather than predicting software costs. So just a little bit of history. Back in 2012, we started a multi-year research project to answer the mail on DoD's request for their requirement in the WSERA Act of 2009 that all large MDAP programs create full cost estimates prior to milestone A. And so when we looked at that in 2012, we're like, wow, you know, that's very different information is available at that point early in the life cycle. The existing cost estimation machinery is not going to answer the mail. And so we put our heads together, and in that QELS research project, we actually took proven methods from scenario planning from Shell Oil. We combined it with Bayesian belief network modeling, and we essentially had a workshop that was eliciting from the experts their subjective notions of factors driving cost and the relationships of those factors. And so that worked out pretty well, except for the fact that in practice, with Space Command and other clients, the lists that we were modeling would be 60 to 80 factors long, okay? And so it was really getting a little bit exploding on us, and we really knew that deep down there was a lot of correlation there, but not necessarily all of it was cause and effect relationships. So in 2017, we connected up with Dave Danks, Richard Shyness in the Department of Philosophy, learned about their discovery algorithms and the tetrad tool, and we decided, wow, this is going to be now an opportunity to pare down what we need to model that's truly driving cost and what would be used to intervene to control cost. And so we've gone from a prediction mentality pre-2017 to a prescription mentality, where now we want to revisit data sets, acquire new data sets, measure new factors, and we want to have prescriptive modeling that will let us take factors that truly are causal on costs from the practitioner level, team and leadership level, the organizational enterprise and acquisition technology, and have models that would actually enable people to change outcomes. It would be very useful for price and contract negotiations and a lot of things. So that's the journey we're on with this project. Just some preliminary results here from the SCOPE project. You can see that we've analyzed a number of different historical data sets. These were on different research projects. One on size, that was with the University of Southern California, on complexity and performance, on architecture violations, and also on team performance. And what you'll see is only a small subset of the previously concluded factors through traditional statistics were causal on the outcomes. And so that's really been a big wake-up call, and we're trying to get the word out that we really need to go beyond just traditional correlation regression. We need to have researchers formulating the directed acyclic graph that represents their hypothesis of the relationship of factors, and then actually go after causal discovery and decide what's the causal structure that you really want to study. The takeaway on this slide here is that there's 2 types of feedback we get from this causal search. One is the presence of causal links between factors, and the other is absence. And the absence, I think, is going to become the predominant feedback that we see. I think we will be identifying about 80% of factors as being spuriously correlated, or at least not supported in causal evidence through discovery. So in terms of actual benefits, working with the team, I wanted to put pictures of the folks that we work with here in the Department of Philosophy. The great coaching related to the tooling and the discovery algorithms. They are continuously developing new search algorithms, updating some of the algorithms, and updating the tetrad tooling. So lots of new capabilities there. I mean, I think in the past year, we've had a bootstrapping ability added to tetrads. So it's becoming closer to a production use that we want. we are gaining insight from them as they work on other research projects, like in the medical field with fMRI data. And we actually just recently learned a technique that they use to do causal analysis on that data, and we're applying it to one of our projects. Students are involved with helping with new algorithms and updating Tetrad, and I truly believe we do have this cycle going of research to practice and practice to research. Some lessons learned to mention. I want to be honest that this is still a mix of science and art. We still need to further define and routinize the search strategies that we should use, and I know there's not going to be just one answer for that, but we want to create job aids that help our fellow researchers use this in a more repeatable fashion. And I think there's still opportunities that we're learning from our CMU brethren on how to further integrate machine and causal learning. And the last two are more administrative, but we're learning to engage with our CMU partners much earlier in the SCI research process and to do a better job of delineating our fundamental versus restricted research tasks so that students can be involved. So just a couple ideas, the near-term thoughts we have on applying causal machine learning. In the area of simulation and test, DoD has a lot of large, complex systems that are so large that they like to use simulators to test the system. But the problem is, if it's that complex, the experts aren't sure what the expected result is for a test scenario or test case. And so one of the methodologies that's growing in favor is called metamorphic testing, and that's a testing technique that is used when you don't have an oracle of truth, and it's a methodology for defining a surrogate answer to what the testing result should be. The problem is in the literature, the academic results so far, it's very manually intensive. It would never scale up to a DoD system we're dealing with. So we have notions of using machine and causal learning to let that methodology be scaled up. In the sustainment world, we have ideas on using a combination of machine and causal learning to support sustainment, specifically in reliability modeling, reliability diagnostics, in how some of the services are controlling the use of their equipment and scheduling maintenance. And so we think there's a big opportunity there as well. For the long-term future, we brainstormed ideas in the 4 quadrants that we are categorizing our SCI research. So there are a lot of topics going on in the SCI for research and insert, and I really think the opportunity there is to go beyond prediction and classification and actually go into causal modeling and the prescriptive modeling that our stakeholders can use to change outcomes. And specifically on this slide, I wanted to note that there is a concept of explainable AI that David mentioned. I know Dr. Jensen at UMass is working that quite a bit, but we think there's a real opportunity to use causal learning to help explain what to expect out of an AI solution. And then Pearl has a book come out this year, Book of Why, and he talks about a notion of strong AI, and that is that you would need to marry up causal learning with machine learning if you really want to approach human-like intelligence. Okay, so that's what I had. I want to make sure I left time for questions. So, David? Thank you. Yeah, Jeff.
Slides back, you had all of the things that, the attributes that were causal, and many were not.
Yes.
You didn't tell us what they were? You're killing me here. This would have
I
been
did
the
bring my
highlight.
business card, and we have team members here. The one that I specifically worked on was with Rick Haseman on the architecture violations. They were studying 4 architecture patterns that Drexel had automated on whether it's being violated or not from static code analysis. And of the 4 patterns, the one on cyclic dependency was the one causal on the quality outcome that they had, and the other 3 were not. Improper inheritance. Okay,
Yeah.
I will. Yes?
On the complexity one, that was my dissertation.
Yeah.
That we reworked and ran through such that the 3 factors that
And just to do a quick, just to make sure to emphasize a point about this particular slide, so the of 4, of 3, of 4, of 20, those, as you said, those were all highly correlated with the thing we cared about. The way to think about this is that we'd identified a lot of symptoms, and it turned out only a couple of them were the causes of the problem. So they are indicative if what you want to do is simply predict, is this project going to go badly, for example. Stakeholder relationships are a really important way to be able to predict, is it going to go badly? But if you want to fix it so it doesn't go badly, that's where you need to have the causal knowledge. So it's not that we had wasted our time with the previous things, it's that they give us a different kind of information than we might want to normally have in some contexts.
Other questions?
Going once, going twice.
All right, thank you.
Can get ahead of schedule.